once again, we're looking at a problem where a car or a particle is going around a track. And these are common in these types of problems because acceleration is constant. And with constant acceleration, you get a nice circle, and that often implies a track. So, looking at this problem, we'll figure out what it's actually asking, and then I'm going to give you a chance to pause the video to see if you can work through the equations. The two parts of problems like this that are complicated is figuring out first just what is the problem even asking for, and then second is if you can deal with all the equations. So if you're having a hard time solving this, and once we get through the explanation, if you understand what's going on, see if you can actually do the equation part on your own. Okay, back to this first part though. This question is asking to find the distance between two cars as one car passes the finish line. So if this is the track and one car is passing the finish line, you're to measure the distance here between the two. And that's going to be s because arc length is going to be the magnitude of what that person is traveling. And we can't make any assumptions at this point as of which car, A or B, crosses the line first. Because even though the car A has a shorter distance to go, its acceleration is lower than car B. So one thing is higher in one, and the other thing is higher in the other car. So that is unfortunate. We're going to have to solve for the equations in both of those to determine which car passes the finish line first. And then we can determine the distance. So let's also look at the assumptions. There's a lot of assumption in these kinds of problems that you're going to have to identify, because if you don't identify these problems, you're either going to plug in the wrong values for variables in the equations, or you're going to be missing variables that you need to know. One thing that it tells us is that the speed of the cars is constant. So that means that there is no change in the speed, and that only affects the part of acceleration that changes the speed of the car. And as we looked at before, that is the tangential acceleration, because we're working now with a dynamic coordinate system that changes with the car. So if we have a car here, this is going to be a tangential affected by the gas pedal, and the wheels are affected by a normal. So the only thing that equals 0 is this a tangential. Because it's going around a curve, there has to be a normal, or else the car would be going straight. And because we know there has to be an a normal, that means that the acceleration max that is given to us in the problem is the normal acceleration. So we can put a little mark there to remind ourselves what that acceleration is, and not to put it in for a tangential. In the previous video, we actually solved for a tangential from the original values, looking at what their base components are. So it makes sense that the a normal is going to be solving for the change in position of that coordinate system, because it's solving for the change in theta. So that is exciting because we've already identified something about the problem. Now the next thing that we need to look at, or I guess we could have looked at it first, is when it talks about horizontal, that doesn't mean horizontal in looking at it from the top down. It means that the person is running on a flat surface, because if they are running up a hill, that is a change in the direction of velocity, and when you change the direction of velocity, you have to have some kind of acceleration. So they simplify the problem by reminding us that this car is driving on a very, very flat road in terms of gravity. So that is very, very, very helpful. Now pause here for a second, because now hopefully you understand a little bit more of what the problem is asking for. See if you can solve for it on your own. If not, just keep watching. So let's draw a line here and move on. Now S. We've looked at S before, and before we have converted it to X, which is a straight line. Let's do that now so we can solve through the equations in a more familiar form. So for car A, if this was the X direction and we were to pull this down, this S of A can go along this line and be this S of A. And for car B, you can also take that curve and pull it down and call this S of B, and both of these can be converted to X. This is not necessary, but for when I was working through these problems originally, it helped me to identify them in a flat sense so that you remind yourself that AT is not dependent on direction at all. It is just dependent on the speed. Okay. Now, how do we know what we're supposed to solve for? Well, we have AN and AT equals 0. AN doesn't really go towards the equations that in the very first video of this we derived, but AT does. So from AT, we can derive the velocity, time, and position. But using the dt times d theta dt, we can get velocity from AN. There's not much we can determine about the time and position from AN. We can get those from these equations, though. So this velocity here can lead us towards the other velocity because it's the same in both cases. And then from velocity, we can solve for time and distance. We'll get to this part in a second. First, let's just look at the velocity. Because AT is equal to 0, that doesn't give us much about velocity, but we can solve for AN with velocity. And we know that AN equals V squared over rho. We derived that in the last equation. So for A, we can say that A of AN equals VA squared over rho. And plugging in the given values, and for G we're going to use 32.2, making sure they're right in the right measurement system. And then we'll get that VA equals 76.1 feet per second. And doing the same thing for car B, AN of B equals VB squared over rho of B equals 0.76, 32.2 equals VB over 320 feet, and that makes VB equal to 88.5 feet per second squared. So now we solve for the velocity of both of them. And remember, we're solving for all of these of both cars because we don't know which one comes first. Okay. Now, we have the velocity, and this can also go to x. In a previous video, we don't know whether we're supposed to go to time or x. In a previous video, we found velocity in terms of x, and we also had velocity in terms of time. However, this equation only works if your velocity has time in it. But the acceleration for this part of the problem is 0. So it's not like we have gravity in it to make velocity in terms of t. And because of that, there is no substitution that can be made to make velocity in terms of x. So if you were to use this problem and plug in a normal for that acceleration instead of like g, like we've used before, it will be wrong. So don't just assume because the variable is in the equation that you can use it, because it has to be the correct variable in the equation. So for this case, this is not true. First we have to solve for time, and then we can go to position. Let's do that now. So we know that V equals ds dt, and since there's no change, you can just have it as s over t. And solving for t, it is s over v. So TA equal SA over SVA is rho theta, and that's converting from that radians and theta to the arc length, over VA, and that is 300 times pi over 3, which is that conversion, times 76.1, and that makes TA equal 4.13 seconds. For T of B, you'll do the exact same things but with the different variables. So rho B theta V B equals 320 times pi over 3. And for this, the velocity is 88.5 meters per second. And that makes T of B equal to 3.79 seconds. And at this point, we can now make an assumption about which car is going to cross the finish line first. And that will be car B, because they reach the finish line at 3.79 seconds, whereas car A reaches the finish line at 4.13 seconds. So now we've solved for time. Let's look at position and then see how far the cars are from each other. So if this is the track of car A and this is the track of car B, at the finish line here, car B is going to be at the finish line while car A is behind. And this distance is the arc length that we're solving for. And we only have to use one equation. We don't have to do it 2 times like we've done previously, because now we know which car is ahead. B is the first car. So this arc length here, S, is going to be equal to the velocity of A times the difference between the time of car A and the time of car B. And that will be 76.1, 4.13 minus 3.79. And overall, that is going to be 25.9 feet. Now we have successfully worked through all the equations to find which car goes first and the distance between the two. So good job. You guys did great. So looking back at this problem, let's talk about the complicated parts. So one is to know that constant velocity means that the acceleration tangential is 0, and that the maximum acceleration that's given is a normal. The next thing is not to assume which car goes first and that you have to solve for it. The third thing that is complicated about this problem is knowing which equations to use and to not use incorrect variables. First, you have to identify that you solve for velocity through a normal, because that's the only acceleration that you're given. Then you go over to this other track of deriving equations, because at that point you can get time and position from velocity. However, you have to make sure that you remind yourself over and over again that A tangential is 0. And because of that, you have to solve for time from velocity, which we did, and then you can solve for position. You cannot go directly from velocity to position like we've done before. Remember, you have to have an acceleration that equals a value for tangential. And we don't. So that's how all of these problems are the same and yet very different from one another, because the assumptions and the knowing how to use the equations and what the equations mean. And that's why I found it useful for me when I went through the class to go through the derivations of where the problems came from, because then, based on the assumptions, I knew which equations to use. If that's not helpful for you, you can learn it in different ways, but that's how I found it helpful, so maybe you can learn something from it.